Okay, a pointer. My name is Oleg Ermakov, and I work with MTS Mobile Telesystems. I've been with this company for 20 years or so, and for 20 years or so, I've been in charge of data transfer in mobile networks. My presentation is about our experience of deploying IPv6 in our mobile network. So let's go. First, I will talk about the depletion of IPv4s and the need to transfer to IPv6, how to cook it, our cooperation with RIPE NCC, routing of IPv6 routing. I will also discuss some of our early experiments with IPv6 on the mobile network. No, it's a joke, really. This is not the true content of my presentation. I will dive directly into the technical part of the presentation. What you see now is the structure of the backed core of our mobile network. It looks pretty scary. There is probably only one word that you understand written here on the page, the internet. But we start from the left. On the left, you see icons visualizing base stations. They are indeed base stations. GPRS grun, that includes the base stations themselves and their controllers. The next generation of the network they had their own RNC controllers. The LTE base stations do not require a controller, and they connect to the mobile core as is. The next bit of this picture is the backed core that provides for the mobility and sessions. It's responsible for mobility management and sessions management. In 3G, we used SGSN, which registered subscribers, and SGSN then decided where to land the session on every access point. In LTE, we use MME, Mobile Management Entity. It's a little device, a box, that monitors the state of the subscriber in the network. It manages handover between different access points, and it also decides where the traffic of the subscriber should land. The next segment is called subscriptions and charging. It includes HLR and HSS. It's a huge box that contains identification keys for every SIM card installed in our devices. And this box also contains all subscriptions of all subscribers in the network. Even the mobile number, the way we know it, +1212, is stored in this box. The box also knows about the services attached to a particular SIM card or a particular subscriber. What are these services? Incoming voice, outgoing voice, the possibility to register in international networks, text messages, sending and receiving. It also has the data about packet data transfers, the access points that are authorized for a particular subscriber, and the so-called quality of service profile for that particular access point, which means the speed and how the traffic generated by the SIM card should be handled. The next box is Pcrf, policy control function. It also contains a profile of a subscriber, but in a different dimension. This particular box knows to which internet services the subscriber subscribed. Say a free messenger. Pcrf will know about it, and Pcrf will decide what to do with that particular traffic at this gate. And OCS, online charging system, the last box in this segment, it counts the traffic that goes through the gate, and it is differentiated by services or across the services that it receives from Pcrf. CGNet, I think you all know what it is. I was thinking how to call this bit of the network. I decided to call it WAN. I think you two understand what I meant to say. So let's remove all the unnecessary bits. And let's see how traffic is channeled through this scheme. So we have a phone that uses 3G. It doesn't really matter whether it's 3G, 2G, or 4G. So our phone is identified by a 3G base station, and it goes through authentication. We must understand what's this SIM card about. The base station sends a request to GSN. At GSN talks to HLR HSS to receive some key information. All these elements do the computing of this information. If the keys match, the SIM card is recognized as authorized, and then it is registered. It's registered or attached to the network. Again, the mobile device then sends a request to attach to the network. This request is then channeled to a GSN. The GSN box talks to HLR HSS and now retrieves the complete profile and subscription of this subscriber. These are access points, the type of access point, IPv6, IPv4, and COS. If everything's okay and there are no bans on attachment, if we are in the international network, our SIM card might be prohibited from registering in an international network, for instance. But if there are no restrictions like that, the attachment happens. And from that time, SGSN will track the state of the device regardless of its current position in space. And then the packet session is activated. First, the request goes to SGSN, and now the phone says which exactly access point it wants to engage. We use MTS.ru for mass market, and the smartphone will then say that it would like to connect to MTS.ru using IPv4. SGSN will search for the gateway to which the traffic will land using signal interfaces. The gateway is contacted. The session is up from the radio subsystem to the gateway. Why am I using different colors on the slides? The signaling lines here are shown in black. Blue identifies transport lines. They are traffic bearing or carrying lines. And for historic reasons, the blue lines take the traffic in a tunneled manner from the radio subsystem to the gateway. In our example, we've got an address in the IPv4 version, and the tunnel is built from the handheld to the gateway. The base station knows nothing about the specific IP address assigned to this device, and In fixed networks, they would participate, but in mobile networks, they would not participate in routing of this traffic. Tunneling is cleaned off after the gateway. This is where clean traffic emerges. And at this point, to get it online, to get into the internet, the traffic must be cleaned. It should become white. Now, let's take a look at the IPv6 case. The same tunnel can carry IPv6 traffic. It's basically the same tunnel, it's just that it's a different type of tunnel. And the smartphone should request an IPv6 type of connection. The base stations, again, know nothing about the IP address assigned to the device. The base stations are not involved in transferring this IP address from station to station. All of this takes place in a tunnel. And in order to get online, a rather thick tunnel is built. IPv6 needs no translation, and it gets to the internet in the shape that it was originally received by the device. And the very same tunnel, again for historic reasons, is capable of carrying dual stack. The type of the tunnel will differ slightly, but for signaling purposes, only one number changes. And this tunnel will be operating in a dual stack mode. Now, it is a difficult choice. What does the network do? What do we do in the network? Do we have an IPv6 only? Of course, it would be excellent, it would be perfect, but since in our use case, we had to cut our costs on address translations, IPv4 addresses we are limited in the pool of addresses there, because if we don't expand the pool, Google and Yandex will start showing you the capture screen, identify all traffic lights and all of that, if you see any. So we decided to go ahead with dual stack. It was the simplest and the cheapest solution. When it only started, in the early releases of specifications and recommendations guidelines to build mobile networks, it said that to build a dual stack solution, we had to have two bearers. One for IPv4 bearer and the other for IPv6. Starting from 3GP9 release, we no longer have this problem. There is just one tunnel, and in this tunnel we can transmit both IPv4 and IPv6. No additional licenses are required, and the capacity is not overused. I mean, the capacity of the gateway. Now, what we needed to do to have this arrangement running in our network, the radio subsystem and the boxes that service the Generation 4 networks are very well maintained. They are, I mean, when I say they are well maintained, I mean the software versions and I mean the hardware. So we didn't need to upgrade those subsystems much. There was a trick that we had to apply, but I will go back to it later. SGSN was the box that we did have to upgrade. It serviced the second and the third generation networks. I just wanted to remind you that. And in order to have dual stack running there, for every radio network controller, we had to add one more command, which would say that at this particular base station RNC, dual address PDP should be supported, a tunnel with two different addresses. And now we come to a but. Maybe you heard about femto sort of. It's a box that you can buy. That you can buy a femto cell. It's a miniature home base station. It's a base station for households. I mean, if you have bad connection where you live, you can install this femto cell and have a better connection. But the problem is the current femto cells in the market do not support this PDP solution. So it was the only problem that we had, and some of the Moscow metro lines use those femto cells. We couldn't do anything about it for now. We enter the subway with dual stack and we exit the subway with IPv4. The way to fix this problem is to switch your mobile device off and then switch it on back, or set it to a plane mode and back. But we couldn't find a better solution for it now. The classical version supported IPv4s or IPv6, but we managed to implement a dual stack, which had to be installed on every access point. Billing, the terrible word. On this picture, you see only one box saying billing, but in reality, there are many boxes there. Provisioning was important for billing, and it's one challenge that we had. We had to upgrade a particular access point of every subscriber to turn it to a dual stack enabling device. This link from billing to Pcrf, we use this link to manage policies, PCC rules, and those PCC rules also had to be edited when we switched to dual stack. Because of IPv6 PCC rules, those rules are provisioned for every subscriber to the gateway, and then the gateway, its traffic detection function or DPI, it will know what to do with this access point and how traffic can be let through and how billing will be done based on the rules that it received from Pcrf. This interface is used for an online exchange of data about the subscribers' traffic, of what kind of traffic it was and how much, and then this information goes to billing, this dotted line. We also had to make some improvements here just because we needed to enter a new field, IPv6. Nothing extraordinary, really. And the most dramatic changes were enabled at the gateway. The gateway had to be upgraded, its interfaces, so that it has access to IPv6 internet. After that MTS.ru access point, we use it for mass market clients. In it, we encoded dual stack support and IPv6 address pools, big enough never to think about extending them. IPv6 DNS routing was also included, and the DPI rules, because now there were resources that had to be tracked not only using IPv4 addresses but also IPv6. You all know that no dramatic changes are required for the DNS server for IPv6 to run. It's quite capable of resolving Quad A records, even if the addresses are IPv4. But the practice showed that if addresses are not shown to the DNS server in the IPv6 format, this address will not be used. We had such mobile devices, And in a mobile network, DNS must be IPv6 enabled. And the last more complex bit of my presentation is the CDR collector. We didn't have to tweak it too much. We added a new field, IPv6, and the field that we used to have to send IP addresses of the subscribers to billing and to other systems. Now this field also showed the IPv6 address, but an extra field was also added where the current IPv4 address is recorded. So that was the difficult part of the presentation. Now it will become simpler. RIPE NCC and all other guidelines tell you that every subscriber gets a /64 block. A small allocation is just not, feasible, which is probably right. What happens to bigger prefixes, I will explain a bit later. The mobile router release 10. Yeah, I will rush through the presentation. We support prefix delegation. Prefix delegation sends long prefixes to the mobile router or device. And you can use it in your own interfaces or the guest Wi-Fi network or the Ethernet network. We tested this technology in our network, but we do not have mobile devices. We haven't, therefore, deployed it yet. Vendors. Android IPv6 is IPv6 enabled out of the box, but you have to change access points and type of protocol from v4 to v4v6 in the settings. We contacted all major vendors of Android-based phones, and we asked them to enable the setting by default for our network. And we also changed our profile manually, and all vendors of Android devices will, from now on, use a dual stack setting by default. Apple also supports it, but users cannot manage that setting manually in the phone. This can be done centrally only, and starting from 11.3 version, this setting is IPv4, IPv6 enabled by default for our network. Windows, I don't have much information about Windows because we don't have too many of those devices, but they too support IPv4, IPv6. The type of protocol is changed from IPv4 to IPv4, IPv6. We also have an option of providing access to IPv6 only. If you enable it, the system of privileged ports will be enabled. We had long discussions about whether we wanted to do it or not. We decided to experiment with it, and time will tell whether our decision was right. We see our current IPv6 address. We can see that the provider is MTS. Many people say, hey, I'm running IPv6, but actually it was Google, Google proxy, and not us. The modem mode, I'm sure you all use this mode in your smartphones. You know that you can share your Wi-Fi with other devices. Our mobile device has a /64 prefix. It takes several addresses for itself out of the block, and when sharing Wi-Fi with other devices from out of the same block, IPv6 addresses are assigned to as many devices as is required. I'm showing you 2 devices here only, but you can see that you see how the addresses look like. IPv6, Moscow, April 2017, most of the regions in the Far East, October 2017. In March 2018, we covered all of the Far East and activating or enabling IPv6 for about 5 million devices. Most of them were iPhones and iPads. Happened on the 9th of August last year. And approximately from this time, we have been observing a growth in IPv6 traffic. We've been monitoring it with AppNIC. I don't know why this trough, but with Facebook, this is what monitoring says. We started on the 9th, and this is the 10th of August. 5 million devices provisioned, and after that, a steady increase. Preliminary results. I will show you the data for Moscow and the Central Federal District, which is Moscow and 16 other regions in central Russia. IPv6 traffic in that region is roughly 20% of total traffic. Mostly it is generated by YouTube, Instagram especially, Google and Facebook. Over here you see a tiny line, which is Apple. Apple is still employing its 17th net in the first octet IPv4. Yandex accounts for about 5%, and all of RUNET accounts for not more than 6% of IPv6 traffic. Why not v6.com is a resource that accumulates statistics on IPv6 usage. And this is how our country looks like. These are the resources that enable IPv6. Mail is okay using IPv6, but the resources themselves, they still do not support IPv6. So IPv6 is already in Russia, and there is a lot of IPv6 here. We are generating hundreds of gigabit of this traffic, and probably it's time to finally enable IPv6. It's not too difficult for a content provider. Probably you know about the VoLTE and VoLTE Wi-Fi calling. When we implemented it, this is how we did the settings of the network. If the phone for a specific IPN requests IPv4, it gets IPv4. If it requests IPv6, it gets IPv6. But if it's requesting IPv4v6, it's getting IPv6. When we disabled IPv6 for VoLTE, and we did it because we had a problem with one major vendor of phones, so before it happened, that was how traffic was split between the two versions. Much depends on the settings and the phones themselves, obviously, but I hope that this problem with this device manufacturer will be resolved, and when it releases its next upgrade of the software, we'll be able to enable IPv6 once again. Thank you. Oleg, thank you very much. Any questions?
I'll go in English. Is that okay?
Will someone translate for me? Or we need to get your device?
Well, first of all, thank you very much for the presentation. I really enjoyed it. Even though through the translation. I would be very interested to have a chat with you, maybe with Maxim as help and also translating, to help us feed the document that we presented in the previous presentation. So that would be very interesting for our side to do so. I just wanted to make a very, very tiny note. I don't know if it was in the translation, but it's the document that discusses the prefix assignment doesn't come from the RIPE NCC, but comes from the community. So if you feel that there is something that needs to be changed in there, something that doesn't feel right for you, we can discuss it and report it back to the community so that it can be addressed and maybe changed in the next versions of the document. But it's not, I want to underline it, it doesn't come from the RIPE NCC, it comes from the community as a document.
Спасибо, я понял.
Yeah, I get it. Thank you very much. No, it's not. I don't think that we're going to have any problems with speaking the common language. Okay, for me, the source of those, guidelines is not important, and I don't see any need to make any changes to this community-generated document. Prefix delegation is a technology that's tried and tested. Like, it works fine.